Welcome to part 3 of chapter 8, where we're going to jump in at 8.8 catalytic hydrogenation. We're still looking at additions across a double bond, and instead of adding HX or H2O, now we're adding H2. Now this reaction requires a catalyst, and you see platinum on the slide. Other catalysts you might see are palladium, or palladium on carbon, or nickel. Let's try to be consistent here, or nickel. These are all possible catalysts you could use. The result is always an alkane from that alkene. This reaction goes really well. There's no big competing minor products. You usually get really good yield from this reaction. What you want to know about this reaction is that it is a syn addition. That's going to be most apparent when you look at a double bond on a ring. That's going to be the easiest one to see. And if we look at the example on the slide, what's important here to note is that the hydrogens add to the same side. So if your hydrogens are coming towards you, right, that means whatever was there is going to be pointing away from you. You could get both enantiomers here if there are chiral centers that are produced. But essentially, I want to see that you can show me that this is that syn addition. Now, you are not going to be responsible for the mechanism, but we are going to take a look at it. It helps me visualize why this is a syn addition. Here you're just seeing a energy diagram. Catalysts work by changing the actual mechanism, so it might be more complicated with which bonds are breaking and forming and what intermediates are being made, but you're always going to have a lower activation energy, which is going to speed that reaction up, right? More of your molecules have enough energy to get over the hump. So this is the mechanism, right? It looks a little different, which is why I'm certainly not going to ask you to draw this. But we're dealing with a catalyst that's in a different state, a different physical form than our reagents. Our reagents are in solution typically, and our catalyst is a solid. So this repeating block of gray spheres is representing your platinum, your palladium, or your nickel. Hydrogen, when it comes into contact with those metals, the H2 bond breaks and it adheres onto the surface of the metal. So that when your alkene comes along, it will be attracted to that metal surface, which will open up one of your carbons to pick up a hydrogen. From there, then the other side picks up a hydrogen and your alkene leaves. Your alkane product leaves. Because this double bond is flat and it's coming up to that flat surface, one hydrogen adds and then the other hydrogen adds. So they have to add to the same side. It doesn't flip over to grab the second one. So for me, just seeing those two flat surfaces coming at one another helps me to remember that it's a syn addition. And that's really all there is to this one. You might get meso compounds, so you're not always going to have enantiomers. What I really just need you to focus on is that this is a syn addition. Now, there is a section of of section 8 that you are not responsible for. There are other catalysts that will dissolve and won't be a solid surface. Something like Wilkinson's catalyst, there's asymmetric hydrogenation. You are not responsible for that, so you may skip slides 56 through 60. We're going to move into the next section, halogenation, right? We've done hydrohalogenation where we've added H and a halogen. Now we're going to go ahead and add two halogens. So you can use chlorine or you can use bromine, and in either case, you're going to get one of the halogens on each side. You don't really refer to this as mark or anti-mark because you get a bromine on both sides. more substituted and less substituted. This reaction doesn't really work well with fluorine or iodine. You see that kind of a lot. Oftentimes iodine's too slow, fluorine's too fast. You get a Goldilocks situation with chlorine and bromine. They're just right. They're reactive enough, but they're not too so reactive that they're violent. It is important to know that this is an anti-addition. You are going to need to know the mechanism. So we're going to jump into the mechanism, and I'm going to do it over here on the whiteboard, and then I'll show you the slides because I do it just a hair different than Klein. Both would be okay with me though. All right, so I'm going to go ahead, since it's an anti-addition, I'm going to use a cyclic alkene mechanism. All right, there's a hydrogen on both sides here, and we've got bromine. Now, bromine you might look at and think, well, that is nonpolar. How is that going to react? And you're right, it is nonpolar, but what did you learn about dispersion or London forces in Gen Chem? That it is a cloud of electrons and that there's going to be temporary dipoles. And this takes advantage of those temporary dipoles. Now, we are going to attack that bromine. This does break the Br bond, but something that happens here that we haven't seen before, well, we saw with oxymercuration, demercuration a little bit. There are a bunch of lone pairs on that bromine, so even though the bond is breaking between the two bromines, there's still a lot of electron density on that bromine. So as the pi bond is breaking, one of these carbons is going to have more of a positive or partial positive charge, and it's going to attract that lone pair. What can be really helpful to memorize here is this intermediate. So let's say that the bromine is adding to the front. It either needs to be the front or the back, but both of these bonds need to be the same, like wedged or both dashed. Can't have a three-membered ring with a wedge and a dash. This is called a bromonium ion. You've got your hydrogens that were pushed to the back. And this right here allows, keeps it from having any, kind of like with oxymercuration, demercuration, it keeps there from being rearrangements. Then this is actually a pretty good electrophile, and our Br minus that we made in the first step is going to attack. Now it's an SN2 attack, so it's going to come from the back. We can't have 5 bonds on carbon, so the CBr bond here breaks, and that bromine, it's still attached to the other carbon, but it's just going to be pointing out at us. So the product that we make from these arrows, right, this bromine is still on the front side of the ring. Nothing about that changed. Hydrogen to the back. Here, because we had SN2, right, it's going to be an inversion of stereochemistry. That pushes that hydrogen forward, and the bromine that added is going to be in the back. So you always form this 3-membered ring, and then the second bromine adds from the other side, giving us an anti-addition. Now you'll see I do this in 2 steps. Klein, just a little bit different. He shows the bromine adding at first, and then shows this carbocation intermediate. If that exists, it doesn't exist for long because there are no rearrangements. And then it's showing the bromide adding into this p orbital. But it would, if that was the case, okay, I guess that's why he's doing this. If this was the case, you would see anti and syn addition, but you don't. You only see anti-addition. Right, so this looks more like what I've done here, slide 65. You're showing the bromonium coming together at one time. You're showing the bromine attacking in the second step. So it's got to be these 2 steps. That is the only way the anti-addition, no rearrangements is explained. All right, just talking about that backside attack. Now, I only want you to worry about stereoselectivity on rings. That's how I'm going to ask you when I want to know the syn or anti. It gets a little bit trickier when you've got open chain alkenes. And so I've tried to limit what you're asked on your homework, and I definitely won't do that to you on a test. The next reaction is actually just expanding upon this one. So Halohydrin formation, we're still taking Br2 or Cl2, but now we're adding in water. You may see another solvent for halogenation. Let me come back here for just a moment. If you see a solvent down here like CH2Cl2, dichloromethane, or carbon tetrachloride or chloroform, these are all non-reactive organic solvents. They will not play a part. Sometimes you see them, sometimes you do not. If you have water as the solvent, this is really important. This is going to change what product you make. You are going to make something called a halohydrin, right? Because you have a halogen and you have that hydrate, right? That hydroxy group. This is also an anti-addition. And it's hard to say it's mark or anti-mark, but it puts the OH on the more substituted side. So you can see here, there's not a difference in substitution, but we still make the bromonium ion. It's just that the Br minus doesn't attack, the water does. So let's do that together here. I'm going to make an asymmetric double bond. And we're going to show the first step is exactly the same, right? We are going to attack our bromine, the Br2 bond breaks, and then one of the lone pairs in that bromine will also form a bond to the other side of the double bond. All right, so again, let's say the bromonium ion came to the front. That means we would still have a methyl group to the back. Now, when you form Br minus in water, it quickly gets solvated. And so water is your solvent here. You're going to have a lot more of it. It's simply more likely that the water is going to attack. There's just so much more of it. And it's going to attack from the more substituted side, which may seem counterintuitive at first. But what is happening is, especially because it's SN2-like, we don't usually see this, but the bonds are forming and breaking at the same time. This is a very strained three-membered ring, so it is trying to break. And the reason it attacks at this side is because as the bond is forming and the old bond is breaking, you get a partial positive on that carbon. And so where is the partial positive going to be the most stable? On the most substituted carbon, of course, just like we saw when we talked about full carbocations. So this bromine is still coming towards us. It's just not connected to both sides of the ring anymore. The methyl group got pushed forward and the water added to the back. Now we can't just have atoms disappearing. So we do need to show in a final step this proton transfer. You could use Br minus, but more likely, right, again, water is going to be our base. It's just important that you don't make up hydroxide or, something that's not actually there. So we wind up with our OH on the same carbon as our methyl and on the opposite side of the ring from the bromine. Right, and that's our halohydrin formation. Okay, so there's just that explanation.